there, ATS 211 students, Dr. John Troggy, and I'm just here today to present to you the third lecture of our course for the 2017 semester. Last time when we met via Skype, we were talking mostly about contouring. And I understood, clearly you have some experience with that, whether that was in the 114 lab or whether in other classes with me or other classes with other professors. I know that you probably just need more experience with it in order to kind of have more of an intuitive sense of what the contours mean and so on, and to identify when there's problems happening and so on. So we'll get more exercises with contouring, but that's not really where we're going to continue. We're going to eventually be using software to produce contours and so on. Now, everything that we did so far with contours was about surface observations, but now I want to start moving forward and talking more about upper air observations, which are something that most people are a little bit less familiar with. I think most survivors of classes like ATS 113 and 114 or something like that are at least aware that upper air observations are generally collected using weather balloons, which are just hydrogen-filled balloons that float away, carrying a package of instruments called a radiosonde. So like here we have a picture of a launch of a weather balloon going on here, where they've inflated it with hydrogen, and then it's going to carry away this little package. It's called a radiosonde. The radiosonde, I meant to have one out for today, but I couldn't find it. I have some here in my house, I just couldn't find any of them. They're a little package about the size of, I don't know, like a box of macaroni or something like that. And they are very light, and inside of that package there is an electronic thermometer called a thermistor, and other pieces of information, of equipment that measure various atmospheric properties as the instrument is being pulled upward in the atmosphere by the weather balloon, and then radios that information back down to the weather station that did the launching. There's a small battery inside of there and so on, but the whole thing is remarkably light. When I would have students, touch them or whatever, they're surprised. It doesn't weigh very much. Well, of course it doesn't weigh very much. It has to be lifted by a balloon, and balloons don't carry a lot of weight. So what we do is we launch the balloon in this software. I just found some examples where people had used the software to show the trajectory of the balloon. In this case, you can see they launched the balloon apparently in Albany in upstate New York, and you can see the trajectory mapped out here as the balloon rose and then popped and then fell back down to the surface. Sometimes people have a misunderstanding about that. They think like balloons go up and they stay up until they pop or something like that. Well, I guess so, but the whole flight takes like an hour. Okay? The balloon is not going to reach some cruising altitude and stay there. It's going to keep floating and floating and floating upward, and as it rises and rises, the balloon keeps stretching and expanding as it encounters lower and lower pressure, and within an hour or so the balloon will pop and it will come back to the surface. So here you can see a trajectory, a balloon followed after a launch. Here's another really cool one where you can see how the path of the balloon went up and up and up, and then eventually it fell. I like this one where you can really see how it encountered different winds that were pushing the balloon in different directions and so on. Okay, notice the site, one here says that, you can actually, it's labeled, you can see the balloon burst in the recovery site. Just so you actually have more sense of how this is all done, typically when they launch a weather balloon, the flight lasts about an hour, and if all goes well, it makes it up into the stratosphere. Get through the entire troposphere and up into the stratosphere before it pops. The balloon will pop, and as I said before, the radiosonde plummets to the ground. There is a little paper parachute that kind of slows it down. The tattered remains of the balloon as it's falling help slow it down, but the thing only weighs a couple ounces. It's not exactly going to hurt you if it falls on you, or put a hole in your roof if it lands on your roof. Inside, if you're not familiar with it, inside of a radiosonde, there's actually instructions to the public who find it, there's a little mailing envelope in there, and you can put the radiosonde in the envelope, and the post office will take it postage-free back to the Weather Service, where it'll be resurfaced and reused. In practice, the Weather Service gets almost none of them back. They generally end up in the ocean or out in some farmer's field where they get, hit by a tractor or something. They get almost none of them back. But at least they make an effort. And it's a good thing they do, because radiosondes are expensive, a couple $100 a piece in general when they launch those things. So they want to find them as much as possible, but in practice it almost never happens. The instruments on board a radiosonde are not particularly complicated. Basically, there's a thermistor measuring the temperature, and there's an instrument measuring the relative humidity of the air, and there is an instrument measuring the pressure. And that's basically it, okay? But from temperature, pressure, and relative humidity, there are ways you can use the kinds of math that you learned in like an atmospheric physics class to recover, to get anything else you need. I mean, you want to get dew point, you want to get potential temperature. I know you may not know what potential temperature means yet, but that's okay. Any meteorological thermodynamic type parameter you can get if you have those pieces of information. We also get things like the winds from radiosondes and weather balloons, although it's not like as the balloon flies it has a wind vane and anemometer on board. It's simply by tracking the balloon. Okay, we know it moved from here to here over this period of seconds, therefore the wind must be from that direction at this speed. Okay, we just infer it from the coordinates it is at each time. The height of the balloon is actually determined using the hypsometric equation. Again, if you've taken or will take atmospheric physics, you know a little bit about the hypsometric equation as a tool for measuring, determining the height of an object based on the temperatures and pressures that it has observed between the ground and where it is now. So since as the balloon is flying, we know its temperature at every time and then we know its pressure at every time, it's not a trivial thing, but it's kind of a crank-turning kind of thing to get the height of the balloon from that. There are GPSs on board a radiosonde. There are ways that they can use GPS information for height as well, although GPS estimates of height are actually less accurate than the hypsometric equation. They tend to just rather be used as like a as an error checking mechanism. Okay, if the GPS height is radically different from the estimate you get from the hypsometric equation, well then they will do some kind of error checking to make sure that like the thermometer wasn't out of calibration or something like that. Alright, so anyway, we get all that kind of information from a weather balloon. Well, when and where do we launch them? Well, we don't launch all that many of them. They are launched at National Weather Service Forecast Office, where there are actual National Weather Service employees on site. There are no unmanned weather balloon launches or anything like that. Certainly not operationally, maybe experimentally or something like that. So like for example, where you are in Omaha right now, the closest place where they are launching those balloons are at Valley, Nebraska, KOAX, which is, you know, what, I don't know, 10 miles or something outside of West Omaha, something like that. Most National Weather Service offices, nominally anyway, only launch weather balloons every 12 hours. They are generally associated with the times of 0Z and 12Z, you know, 0 Greenwich Mean Time and 12 Greenwich Mean Time, which is either 5 or 6 hours different from Central Time, depending on whether or not it is daylight savings time or not. But basically that means then that the balloon launches in Omaha happen at about roughly 6 a.m. and roughly 6 p.m. They're not, yeah, there's some flexibility. There's a window of time in which they launch them. You might be surprised, though, to see how few places around the country we do launch weather balloons. In fact, I pulled up this map from the Unisys website just this morning, and this is the current network of weather balloon launching sites. And you can see, for example, in Omaha, you're actually quite lucky that in Omaha you're quite close to KOAX. And in fact, in Nebraska, there are 2 sites where they launch. The other one is KLBF, which is North Platte. If you've wondered why LBF is North Platte, it's because the name of the airport is Lady Bird Field. A lot of these codes here are strange like that. There's usually a story behind them. Anyway, but like for example, where I am in Indiana, there are no weather balloons at all. And like the entire state of Utah only has 1. And I mean, there's just not that many of them. It's about 85, 90 locations around the country where we launch these weather balloons every day. And that means that, of course, by necessity, we have much less information about the conditions aloft being like away from the surface, than we do for the conditions at the surface. Remember, at the surface, just in Nebraska alone, we had something like 45 weather stations. There's a few thousand nationwide. Here, we only have a few dozen stations that are launching weather balloons to get upper air data. It's a valid question. Is that enough? Do we actually get the information that we need from this network of stations? Well, frankly, it's going to have to be enough. That's all we get. We aren't going to have the kinds of detailed information about the exact position of all the weather features aloft the way we can get from the surface network. Okay, we have to work with what we have. There's actually kind of an interesting philosophy of science kind of thing behind here, where we're talking about this as being like a, well, the right word is synoptic assumption here. Synoptic as in we're looking at the big picture. We're not going to worry about all the tiny little details of the flow aloft. We're going to be looking at the big picture. You probably know that word synoptic from like a theology class where they talked about the synoptic gospels. Okay, in the synoptic gospels you get a kind of overview of Jesus' life. Not just sort of things he said, but a story of his life. And like synoptic meteorology. Synoptic meteorology means like as in we're taking in a broad overview. We're not worried about every little detail of what's going on at every station. We're just getting a broad, like nationwide picture of what the weather pattern is doing. Well, this is part of what's called the synoptic assumption. We're going to work on the assumption that this is enough observations. And we don't have much choice. I mean, this is what the government's willing to pay for in terms of how many observations we're going to get. You notice, just sort of by looking at this plot, that in fact we can, although don't all that often, we can plot upper air data using kind of a station model type idea. We plot the station models at the location where we launched the balloon. Now, in theory, I mean, over the course of like the hour that they fly, they might end up, 100 miles farther downstream or something like that, but we don't worry about that. We plot the station model as based on where the balloon was launched, okay? And, the station models work broadly the same sort of way that they did for surface station models, where we're going to have like wind barbs that point upwind, and they're going to make little Fs, and they have flags and pennants and so on, and they have temperature plotted to the north and west, and dew point plotted to the south and west. For reasons that have always been mysterious to me, when we switch to upper air data, we use Celsius rather than Fahrenheit. That can always be confusing, but whatever. Okay, it's on there. With some knowledge, you can sort that out. You'll notice that there is a number to the northeast of the stations, much as there was when we were plotting the sea level pressure. That is a measure of how high above the ground that observation was. So, for example, you might not have noticed that in the top left corner of this plot, it specifically says this is 700 millibar data. This is the information that was reported back by the radiosonde when it passed through the 700 millibar level, when the pressure hit 700 millibars. So as the balloon rose, it started off at a fairly high pressure near the surface, somewhere around 1,000 millibars, and when it measured 700 in this case, it reported back what the temperature and the dew point was, as well as a way of figuring out its height. Again, that's actually done using the hypsometric equation, and information about the winds and so on are obtained by triangulating based on GPS coordinates of where it was just before 700 millibars and just after 700 millibars. So we get this measure of height that's to the north and east of the station itself. This is then how high above sea level, actually, the 700 millibar level is at this location here. And it's in a code. So, like, if you look, just because it's a little easier to see, if you look at Denver, Colorado, you see the code is 945. Okay, the ugly story is that's a code, much like there was a code when we did the surface pressures. Remember how we had to either put a 9 or a 10 in front and all that kind of thing? All right, the truth of the matter is the codes are different for every pressure level. Like, I don't know, at 700 millibars, I think you put a 1 in front of it, and then that's meters or something like that. Or you put a 1 in front of it or a 2 in front of it, depending on which one is what makes it closest to 2,000 meters or something. Every pressure level, the 500 millibar level, the 400 millibar, they all have a slightly different set of rules. I wouldn't worry about that, okay? You don't, in general, take a look at these observations on a station model like this for upper air data and like come up with an interpretation based on the heights. So that I wouldn't get bogged down in. I just wanted you to be aware that it's there. But they use a different code for every level, and memorizing that is not what you're interested in, and it's not what I'm interested in teaching, that's etc. Okay, so these observations are taken twice a day at about 85, 90 stations around the United States, a few hundred such stations worldwide. And of course they have to be shared. I mean, that's the nature of weather observations, is we use the local data manager, and that's the LDM software, to transmit this data around the world to all kinds of different applications. For forecasting, for climate modeling, for climate monitoring, for all kinds of, for lots of purposes, okay? Flight operations, and so on. So the data have to be transmitted, just like we had to transmit the surface observations. The software that runs the unmanned weather station had to find a way to transmit the surface data observations, and we have to do the same thing for the upper air observations. And it's probably not terribly surprising that once again we talk about the fact that there are two different ways to do it. One is again a form of buffer, where buffer, you remember, is this binary format. It's very modern. It contains all kinds of metadata in there. For example, the make and model of the radiosonde that took the observations might have the names and background of the people who did the observations. It might have calibration data. All kinds of metadata like that can be obtained from the buffer report. But they're also in binary. There's nothing you can do to look at it and make sense of it. And then, much like there was METAR, that was sort of this this ASCII text-based, keyboard-type symbols code for understanding the report. Well, we actually have that too for upper air data, but it's a whole lot more complicated. There's a series of files that get sent in this ASCII code that, they look pretty manageable. I'll show you one in just a little bit. And they have 4 or 5 different code blocks called TTAA, TTBB, PPAA, and PPBB, which are all horrible names to try to say. But, just to show you what they look like, they're big, ugly blocks of text. So, like, for example, this is the TTAA block for Omaha, KOAX, on the particular day I took this observation from. I don't remember which one I downloaded here. But this is the TTAA block. And then there is 5 lines of 5-digit numbers. And each one of those 5-digit numbers means something. I think, well, the first couple ones are like times and dates and WMO identification numbers for the station and so on. And then there's various codes that represent like the pressure and the temperature and the dew point and the winds. And so actually I think some of those are in the PPBB or the PPAA or the whatever. But this is somehow decoded into an observation of the temperature and the pressure and the winds and so on at all these heights. And nobody wants to do this. I completely understand that nobody wants to sit here and try to decode all of this. That is a thing. Okay, I did some Googling and found that some universities, at their classes, they actually do sit down and decode these things. But it's very error-prone, and figuring out how you decide which pressure level all of these are and so on, that's just not so important. But there is actually a kind of a keen insight that you can gain about these upper air observations by looking at those reports. Remember I said that there were like 4 different blocks. There's TTAA, TTBB, PPAA, PPBB, and I think there's actually a 5th one that's sometimes reported too. I can't think of its name right now. Well, one of those sets of blocks, for example, I think it's the TTAA, is the so-called mandatory levels reports. There are certain heights, pressures, above the ground where the balloon must report, the balloon is reporting, whether the actual code that goes out must include that information. These mandatory levels are 925 millibars, 850 millibars, 700 millibars, 600, 500, 400. There's about 14 of these levels altogether in the troposphere. They're specific pressures that the balloon reports the conditions at. And those mandatory levels are coded up in one of those blocks. I think it's TTAA. So that weird code that we were looking at before with all those 5-digit numbers, somehow or other, if you sat down and decoded each of those 5-digit blocks and did it all right, you get the temperatures, pressures, and winds and so on, and the humidities and so on at the mandatory levels. Okay. Now, but there are other heights above the ground that we are also going to be reporting to, and these are the so-called significant levels. I think they're in the BBs. I think it's TTBB and PPBB contains information about what's going on at the significant levels. And the significant levels are something that gets figured out based on what the radiosonde is seeing. They're going to be places like levels where the lapse rate is changing. Remember that word lapse rate, how temperature is changing with respect to height? If we start hitting a temperature inversion, that's a significant level. So the balloon will report, the station will report, okay, at this pressure level we encountered this temperature, this pressure, something significant happened there. Same with a level when we pass through where the winds are shifting speed or direction rapidly. Or when we pass through the tropopause, okay, the balloon must report back when it went through the tropopause. And there's a few others of these rules that make the significant levels. So when you launch the balloon, the software that is running the data collection and so on will keep track of all the mandatory levels, where the balloon must report back, and all the significant levels, places where something is happening, like you're going into the bottom of an inversion, or you're coming out the top of a temperature inversion, or something like that. See, here's the deal. we don't actually need everything that comes down, gets radioed down by the radiosonde. Most radiosondes are operating more or less continuously as they fly, and they're almost continuously communicating back to the ground station, which means that they actually generally report back with the temperature they're observing, the dew point they're observing, the winds that are inferred from their GPS coordinates and so on, typically every 2 seconds. Alright, 2 seconds of flight time in the balloon is only a rise of a meter or two. Okay, it's not very far. Do we really need to know the temperature, the pressure, the winds, and so on, like literally every 2 or 3 meters as we go up through the atmosphere? For example, let's just suppose, I got a little example here. Let's say that the balloon, when it hit 532 millibars, the temperature measured was negative 5.0 degrees Celsius. And then, let's say a couple seconds later, it measured the pressure of 530 millibars, and it had a temperature of negative 5.1 degrees Celsius. And then a couple seconds later, it measured at 528 millibars, the temperature was negative 5.2 degrees Celsius. Well, I would ask you, did we really need that middle one? I mean, did we really need this information that at 530 millibars, the temperature was negative 5.1? Wouldn't we have just gotten that by interpolating between, if we knew the pressure the temperature at 532 millibars, and we knew the pressure at a temperature at 528 millibars, couldn't we have just figured it out? I mean, did we really need to waste precious bandwidth and so on over an observation that we could have just as easily figured out? I mean, maybe we do need that observation. Like, let's say instead of being negative 5.1 degrees Celsius at 530 millibars, let's say it was negative 4.7 degrees Celsius. We could not figure out that the temperature was negative 4.7 degrees Celsius if all we knew was at 530 millibars, if all we knew is the levels above and below it like we had here. See, we would not guess that the temperature was strange at 530 millibars based on that. But see, then that would have triggered a special observation. Not special, a significant observation. The temperature profile would have included information that we had hit a significant level where the temperature was different than what we expected. So, okay, if the temperature was weird at that level, we would get that information in the form of a significant report. A significant level. But honestly, we don't really need that information for all those individual levels. And in fact, what we really only need are the mandatory levels and the significant levels. All the other levels in between. You want to know what the temperature is at 622.5 millibars? You'll find out what the temperature is at the level above, at the level below, and you'll just interpolate in between. Okay? There's no reason to report all those other levels. It's a way of saving bandwidth and so on, saving archive data space and so on, rather than plot all those levels. This is actually a very good idea. Okay? It saves enormous amounts of bandwidth, enormous amounts of storage and so on to just keep the mandatory and significant levels. Because you can reconstruct the observed temperature and pressure and humidity and so on, winds, at any level as long as you know the mandatory and significant levels. This is really smart. I've actually always been kind of impressed by this plan. Okay, so I don't want you to know how to decode TTAA, TTBB, and PPBB, and PPAA, and all those kinds of things. Let a computer do that. But the idea that we're just documenting mandatory and significant levels from which we can reconstruct the temperature and humidity and winds and so on at any level in the atmosphere, regardless of whether it's actually in that file or not, that's brilliant. Okay? That's a smart plan. Now, because we only have something like 85 stations around the country where we are observing the upper air conditions, it can be challenging to contour this kind of data. I mean, you'll get some exercises with this when we do another assignment that involves contouring, but getting the contours to be pretty and smooth and elegant can be a challenge both for individuals actually drawing it with their pencil and for software. I mean, this is a plot made with WXP, and it is actually the day that I'm recording this, and I mean, this is a 500 millibar chart, and the solid contours on there are supposed to be the height of the 500 millibar level, and you can see that there's a big old cyclone kind of sitting up to the north and east of the Great Lakes and so on, and does that look like any cyclone you've ever seen before? I mean, it's kind of lumpy and not very round, and it can be really hard to contour if you just don't have that many observations and they're kind of far apart. Same with, here's just an example I used WXP to make. This is a 500 millibar chart from a long time ago, but again, I mean, the the contours are not that great. I mean, they're kind of, even for software, even for professional software like WXP, it can be kind of hard to make a plot when you only have that much data, okay? That being said, it can be done. You might be familiar with the kind of charts that I'm showing here on the screen. This is what's called a DIFAX chart. Back in the old days when the charts were actually professionally rendered by in the World Weather Building in Washington, D.C. by the National Meteorological Center, they would actually professionally render the contours. In this case, on this map right here, the solid lines are contours of 500 millibar height. And I mean, gosh, they look like a mathematical equation. They're so elegant and so on. Well, this is a combination of, excuse me, contours that were drawn by hand, contours that were drawn by a machine, and individuals, professionals who actually know how to adjust the contours to make them smooth and lovely and so on. It would be very difficult for an individual to have made contours that were this smooth and beautiful. The guys who survived ATS 315 are familiar with the fact that making contours by machine can produce some pretty ugly looking contours sometimes. You get a lot of like little diamond shapes and stuff like that. This is clearly human assisted. Or maybe it's better to say it's machine assisting a human. Clearly they drew these to be, you know, very smooth and elegant interpretation of what the height field is looking like. Okay, well that's about maps. Excuse me for a second, I have something caught in my throat. Okay, that's all been about maps, but that would not be the only way you could interpret or visualize information that comes from a weather balloon with a radiosonde. It seems like it would make perfectly good sense to want to plot a graph of the information that you got. You know, at my weather balloon as it flew, this is the temperatures it saw, or this is the humidity that it saw, or whatever. And as you visualize what a diagram would look like that you would plot from the information that you got from a radiosonde, it's not so hard to imagine what you would want. You probably want something like height on the y-axis, and you want something that you're graphing, like temperature, on the x-axis, so that you could make a graph of the temperatures you saw with the weather balloon at different heights. That makes perfectly good sense. The problem is, sometimes the world doesn't work that way. Sometimes what seems like it makes sense to you is not what's going to be actually helpful. And I'll show you what's wrong with this idea. Here's a diagram. Makes sense. You want a diagram that looks something like this, so that you can see how the temperature is changing with respect to height. There's plenty of diagrams that look like this in the intro textbook. There's plenty of diagrams that look more or less like this in the intro lab textbook. But are they really all that useful, like from a meteorological point of view and for the operations of a meteorologist and so on? I mean, for one thing, height is not a very good y-axis measure. Radiosondes don't report height. We do infer it from the hypsometric equation, but we don't actually measure it. There's other reasons why height is not such a good measure that I don't want to go into at this point. But the point is, we don't really want explicitly for our y-axis to be a measure of the height above the ground, despite the fact that's kind of how we want to visualize it. We want to be able to think of that as being like a measure of height, but height is not the right tool for the job. Really what we want is pressure. What the radiosonde is actually measuring, it has a tiny little aneroid barometer on board. It's measuring quite accurately the pressure as it goes up. So we're going to want pressure as our y-axis, but then you come across another problem. I mean, it's kind of an easy one to solve, but, you know, pressure, as you go up in the atmosphere, pressure decreases. So, like, having there be an origin to our axis, to our diagram here in the bottom left side, and work its way up, that actually is kind of backward. We kind of want our graph to go the other way. See how I changed the direction of those arrows that are on that that y-axis there? You want the biggest values that your balloon saw, something like 1,000 millibars, to be down at the bottom, and you're going to want smaller values as you go up, so that, you know, up at high altitude you're seeing some low pressure. Okay, all that involves is reversing the y-axis. Okay, it's not the end of the world. Okay, we're still not that far from what we thought we wanted. But there's still problems with this diagram right here. See, like if I just sort of made this a nice piece of graph paper where the y-axis is just linear, where like 1,000 millibars is apparently going to be my lowest level. It might actually be a little bit different from that. And then we'll have 900 millibars, then 800 millibars, all the way up to apparently 0 millibars. at the top, well, that would be nice and linear. I can envision how I would draw this on graph paper. I could envision maybe how I'd make a computer program that would graph this, etc. But is that really the best way to do it? I mean, in reality, these layers are not equally thick. Thick being like the distance from the top to the bottom, like the thickness of a book. I mean, the layer from 1,000 millibars to 900 millibars is only a couple tens of meters thick. The layer between 200 millibars and 100 millibars is a couple kilometers thick. But on this graph here, they're the same thickness. I mean, they're the same visual distance between them. 900 millibars and 1,000 millibars are just as far apart as 200 and 100 are. So you would get kind of a weird, distorted graph where everything would be crammed up near the top. That isn't necessarily what you really want either. Well, the best solution around that is not such a hard thing to come up with. You end up using that your y-axis is sort of distributed logarithmically, where the numbers that are small are farther apart. So like 100 millibars to 200 millibars is a pretty big gap, and 200 to 300 is pretty big but not quite as big. 300 to 400 is a little bit smaller, and so on. It's kind of like semi-log graph paper. Okay, so this actually gets pretty close to actually visually approximating how the curve of temperature in this case is distributed with respect to height in the atmosphere, even though we're not really using height as our y-axis, we're using pressure. Okay, well, this is not a terrible thing. I'm on board. I'm on board so far that this could be kind of what we want to make our diagram that would have information that our weather balloon recovered. I'm on board with that. And in fact, I mean, I've not been drawing the x-axis lines on here, but I mean, if I put those on there now, you could see that if we just had a perfectly normal x-axis line, where, you know, you could find a temperature on the x-axis and go up, and you find the pressure on the y-axis and go over from there, you would have a perfectly normal x-axis on there, and you could have a reversed logarithmic pressure scale on the y-axis, which would be a pain in the butt. There's not exactly a setting to do this in Excel, but it's not exactly rocket science either to figure out how this would work. And this would work. This would be a way to plot information that came from a radiosonde. I don't actually hate this at all. Now, we would have some terminology here. These horizontal lines on this diagram are called isobars. And that's actually a pretty smart name for them, because everywhere, you know, that you would be plotting anything along that horizontal line, the pressure is exactly the same. We have a 400 millibar isotherm, where everywhere along that curve, that line right there, it's exactly 400 millibars. And for that matter, we could use the same kind of terminology for our vertical lines on this piece of graph, kind of semi-log looking graph paper here, where the vertical lines on here would be isotherms, because everywhere along each one of them, it's a particular temperature. I didn't actually bother labeling the temperatures, but I mean, it's just graph paper. Okay, it's admittedly kind of a semi-log type graph paper, but it's just not the end of the world. All right, working with this terminology, isobars and isotherms, though, that's kind of the take-home note here in terms of like terminology and so on. Because then, every single observation that the radiosonde took as it flew corresponds to a point along this curve that we're drawing, right? I mean, I'm just highlighting right now in red one point on that curve. The curve is what you observed. You measured the temperature, all these different pressures, and you graphed it. Okay. It has some temperature that you could infer from the x-axis. It has some pressure that you could infer from the y-axis. Okay, we're on track here. We're starting to get something good. All right. And in fact, you can use this diagram right here to do stuff, to do calculations, or at least approximate calculations. Now, we call that a process. We're going to be like doing something like, what if we warmed the air, or what if we lowered the air parcel, or what if we moved it, or whatever here. Each spot on this diagram is an air parcel. It has a certain temperature and pressure. We can do things to warm it, or cool it, or lower it, or raise it. So like, for example, if I warmed this air parcel isobarically, we would be keeping the same pressure, but going to a higher temperature, as I showed on this diagram right here. And again, that's something we'll be doing. Or like, I could lift my air parcel isothermally. We would stay at the same temperature, but be going up to a lower pressure. Okay? These are processes, an isothermal process or isobaric process. Now, processes like this. If you've taken classes, anything from physical meteorology to whatever, you know that there's going to be ways that we're going to be doing things like changing air. What happens if we warm it isentropically? What if we lower it isentropically? What if we blah, blah, blah? Isobaric and isothermal are not necessarily the most useful of them, but we're headed towards the right idea here. So there's things that we're going to be able to do with a diagram like this. This is a useful thing. A diagram like this is a powerful tool, not just in meteorology, but in science overall, especially in physics, and especially in the branch of physics called thermodynamics. And so this is an example of what is called a thermodynamic diagram. Okay, a thermodynamic diagram, we're using it here to depict the information that came to the thermodynamic state variables like pressure and temperature that came to us from a radiosonde. The idea of a thermodynamic diagram, though, is more general than that. Thermodynamic diagrams have thermodynamic state variables as their x and y axes. Those thermodynamic state variables could be pressure and temperature, but there are other thermodynamic state variables like volume or potential temperature or density and so on. I mean, there's other ways that this can be done in like a physics class or something like that, or even like in some like chemistry courses where they're doing things to different volumes of air in flasks and so on. Thermodynamic diagrams is a useful concept in general in science. This is a thermodynamic diagram, sort of. Strictly speaking, not exactly. Strictly speaking, a true thermodynamic diagram, like if this was physics 4.0 whatever that is thermodynamics or whatever, they would be a little bit cranky with me calling this thing a thermodynamic diagram, because although it's true that its x-axis is a state variable, namely in this case temperature, and its y-axis is a state variable, in this case pressure, in practice there's other properties a true thermodynamic diagram has to have that this particular diagram that we've drawn here does not quite meet. Okay? But meteorologists don't tend to use the word thermodynamic diagram so stickly, prickly, exactly finessed like that, the way like a physicist would or something like that. Okay? Strictly speaking, though, the type of diagram we just drew doesn't quite meet the definition of a thermodynamic diagram, but a meteorologist is going to use it that way. Okay? Just so you understood an idea there. Now, this particular type of diagram that we have been building as an idea in this lecture has a name. It's called a Stuvey diagram. S-T and then a U with the two dots above it. That's called U umlaut. S-T-U umlaut V-E. A Stuvey diagram. And a Stuvey diagram is a type of, well, I'm going to say a type of thermodynamic diagram, but somebody in physics will get cranky with me. Okay, it's not exactly a thermodynamic diagram, but it's actually pretty darn close. And as it happens, it has a perfectly regular x-axis with nothing fancy schmancy going on it. And the x-axis is temperature when it's a Stuvey diagram. And the y-axis is just kind of, it's related to the log of pressure. It's the log of pressure, but reversed. Okay. It's called a Stuvey diagram. For what it's worth, by the way, Stuvey diagrams are named after the guy who developed them. His name was Georg Stuvey, and he lived like around the turn of the 20th century. And he was a meteorologist in Germany who came up with this type of diagram as a way of visualizing the data that came from radiosondes. And let's not minimize how big of an idea that was. I mean, prior to like being able to have instruments that could radio information back, we didn't really know very much about the atmosphere above the ground. I mean, we had some manned balloon flights. We had some scientists who had some experimental instruments that could like record on paper as they flew. But basically until, you know, like the 1920s or something like that, there really wasn't any systematic way to do this, okay? In fact, even some surprisingly big features of the atmosphere weren't discovered until pretty late when we had a systematic way to make observations with radiosondes. For example, the tropopause. Well, gosh, we learned about tropopause literally the first lecture of ATS 113, but until you have a systematic way to actually measure things in the atmosphere using radiosondes and weather balloons, there's no way to know there's a tropopause up there. Okay, Léon Tesserandibort was the name of the French balloonist who figured out a way to measure this, and it was like the late 1800s that he figured out that there was a tropopause up there. Alright, so Stuvey diagrams, they're a thing. Meteorologists know about Stuvey diagrams by going through the same process of thinking that we just went through in this lecture of thinking through what would I want it to look like. And here is an example of a Stuvie diagram. Now, you'll notice when you look at this diagram here that in addition to the kinds of the horizontal lines and the vertical lines that we're used to thinking about already by having seen the first part of this lecture, you'll see there's also like orange dotted lines on this one, and there's some kind of green slopey lines, and if you actually look closely, you can see there's some sort of light blue curved dashed lines. So don't look at any of those right now. That's not where we're going with this. For now, just notice the horizontal blue lines that are isobars, and the vertical blue lines that are isotherms. And you'll notice that the isobars are kind of spaced weirdly, where they get closer together down as you get down towards the lower atmosphere, and as you go up through the tropopause, they get farther and farther apart because they're actually distributed logarithmically. Woo! Okay, I mean, again, don't do your best not to look at the orange dashed lines and the blue curved lines and stuff that are on there yet, because that's all still to come. But okay, it's a diagram. And we could use we can plot them by hand. We will plot them by hand at some point. But I can just use software. In this case, it's WXP's component of the software that's called SoundPlot that plots sounding. And I could plot the sounding that comes in from a given weather station, in this case KOAX or Valley, Nebraska, on here. And there's a lot going on this particular Stuvie diagram, so let me just highlight. With orange there, I've roughly highlighted the temperature information that the radiosonde observed. If you notice, by the way, kind of near but a little bit off to the left of the yellow curve that I just highlighted, you'll see that there's another curve that kind of looks similar. That's actually for the dew point, but we'll get to what you do with moisture variables on a different day and so on. But here is our temperature data as we go up, in the atmosphere. This is what the balloon saw. This is its observations. And we can look at this and see things on it. For example, just using the big thick lines that I drew on there that trace the path of the temperature with respect to height and so on. Oh look, down near the surface, near 950 millibars in Omaha, see how there's a little area where the temperature is going up with respect to height? That's a temperature inversion. Not a terribly exotic thing to see at the surface. Certainly not in February, where we are this is February of 2003. But, okay, I see a little temperature inversion. Isn't that precious? We saw something on this Stuvie diagram. We saw a layer of the atmosphere where temperature was increasing with respect to height. And oh look, if I look more closely here, I can see, for example, see how the temperature was decreasing with respect to height through most of the layers of the troposphere, and then all of a sudden around, about 275 millibars roughly, from there on up, the temperature is kind of just wiggling around. It's actually pretty close to the same temperature from there to the top of the graph. That's the tropopause. Okay, the tropopause is at about 275 millibars at this time. Officially, it was 279 millibars, actually, according to the information on the side of the graph there. So, if the balloon continued to fly beyond the top of this diagram, which I think is 100 millibars, it would have been getting up into the stratosphere and seeing temperatures actually increasing with respect to height. Okay, that's lovely. Charming. We've discovered things by using our Stuvie diagrams. And it sounds nice. But there's problems, okay? Stuvie diagrams are kind of close to what we thought we wanted when we wanted to plot data that came from a weather station that launched a weather balloon. But there's going to be problems with all of this. I mean, now, I realize that they're a little small on your YouTube window here, but if you pull up the actual PowerPoint presentation, you can see here that what I've given you here is two different Stuvie diagrams. They're at the same time and the same day. They're both the 11th of February 2003, because I have this old data file sitting around. The one on the left is Omaha, and the one on the right is Miami. And those are both plotted as Stuvie diagrams. Okay, so two different locations that plotted their observation. And there's actually I don't want to minimize it. You're going to see I'm going to turn kind of negative on the whole Stuvie diagram thing. But right now, I mean, in fairness, there's a good old Georg Stuvie. He did a great job. There's all kinds of great things I can see on this diagram here. For example, if I just take a look at these two diagrams here, remember how we thought that at Omaha, the one on the left, we could see the tropopause at about 275 millibars? Well, actually, if I look at the temperature curve on the Miami one on the right, temperature just continuing to decrease all the way up to the top of the diagram. Wherever the tropopause is at Miami, it's more than 100 millibars. It's higher above the ground than 100 millibars. So the tropopause is higher in Miami than in Omaha, if you're survivor of lots of other classes. You're not surprised by that. In general, warmer, more tropical places do tend to have a higher tropopause. Okay. Lovely, I guess. I don't know. We found some information using a Stuvie diagram. For that matter, it's kind of a little hard to see because I positioned them to the left and right of each other. If I had them above and below each other, it'd be easier to see that clearly overall the temperature profile is warmer in Miami than it is in Omaha. I'm sure you're shocked by that. That in February it's warmer in Miami than in Florida, than in Omaha. But again, I mean, okay, we could get that information. In fact, we could even get actual temperatures at different heights and so on from these diagrams here. Yeah, okay. It's not a very high bar as far as like what I would expect of my thermodynamic diagram. I think I should be able to tell that like the atmosphere is different in Miami than it is in Omaha. But I'm kind of down on this actually, because honestly it's kind of hard to see the differences between these two Stuvie diagrams, at least until you've had a lot of experience. The Stuvie diagrams, you know, at first blush, if I just showed these to somebody with no experience at all, they'd say these two diagrams look an awful lot alike. Yet we know clearly there's going to be big differences between what's going on in the atmosphere in Miami versus what's going on in the atmosphere in Omaha in February, right? These diagrams look surprisingly alike for two diagrams that should be telling us, you know, these two places are very different. Let me give you kind of the defining example of what's wrong with this diagram here. That curve that we draw that shows the temperatures that we saw with respect to height for the radiosonde, the slope of that curve is a measure of the environmental lapse rate. That is how temperature is changing with respect to height. Okay, the slope of that line has units like change in temperature over change in height, so units of like degrees Celsius per kilometer. Okay? That is an enormously important property of the atmosphere. The environmental lapse rate is one of the most important things to know about what's going on in the atmosphere at any given time, because that's basically another way of saying how stable the atmosphere is. Stable as in like how easy it's going to be to form clouds and to have precipitation and rising, in general, to have vertical motion in the atmosphere. Well, so the environmental lapse rates, I mean, a fairly wonky term that meteorologists are going to care about and so on, but then again, that's who we are. And we need that information from these diagrams. We want to know how stable the layer is by looking at the slope of these temperature curves that are on these Stuvie diagrams. Okay, well, if you look real close at the one for Omaha, I kind of highlighted a stretch of it there. Okay, in yellow there, you can see that near the surface there's a temperature inversion, where temperature is actually increasing with respect to height. The slope of the temperature curve is actually leaning off this way. That's actually an environmental lapse rate that's negative. It's extremely stable. That's a temperature inversion. It's going to be hard to form clouds. It's going to be hard to get precipitation. So in general, it'll be hard to get vertical motions. Okay. In contrast, like again, I highlighted a little farther up in the Omaha graph there. Here's a layer of the atmosphere where the temperature, the curve profile is sloped the opposite direction, sloped this way. And at this layer, the environmental lapse rate is positive. It's going to be less stable. It's going to be easier to lift and lower air parcels. It's going to be easier to make clouds. It's going to be easier to make precipitation, etc. And actually, if you take a look a little bit above, I didn't make a separate slide to show it, but a little bit above that layer, you can see that the environmental lapse rate tips a little bit more towards vertical. That is it's going to get a little bit more stable and so on. If you don't have experience with what I'm talking about here, basically, the more the slope of the sounding is sloped like this, the less stable it is, and the more it's sloped like this, the more stable it is. Okay, so use that little key that I just made right there. That'll help you understand. So that slope is the difference between clear and cloudy. It's the difference between rain and no rain. I mean, that's something we really want to know, how steeply sloped that environmental lapse rate is. Well, let's go back to our diagrams here. Well, if I was actually looking at that temperature curve on Omaha and looking at that one in Miami, boy, I mean, you know, individual layers along the way, excuse me, it might be a little bit different. But you know what? Actually, on these Stuvie diagrams, except for in the temperature inversions itself, pretty much all the slopes look alike. I mean, They're different, but the difference is small on this diagram. The difference between like sloped enough that on a Miami day there might be showers because there's some instability and there's some rising air parcels, versus it's a cold, clear winter day in Omaha. The difference is like the difference between this slope and this slope. I mean, I can barely tell the difference. This is just not the right tool for the job. I like what I wrote here. For a STUVI diagram, while technically you can infer the stability from the slope of the temperature profile on the plot, in practice, most of those times the slopes are just quite similar, even for quite important differences in stability. This is just not the right tool for the job. The difference between stable and maybe having clear conditions and unstable and you could have severe thunderstorms is just too small to see with your eye on a STUVI diagram. Just to kind of give an analogy here. Oh, I'm sorry, let me get here. I mean, so STUVI diagrams here, they make a lot of sense in terms of how we built them. Oh, we came up with this plan, just a perfectly regular x-axis of temperature. The y-axis we had to get a little fancy with using the reversed log of pressure, but overall it wasn't that big of a deal to think it all through. But in practice, they're just not so useful for the kinds of things meteorologists actually do. I mean, when we actually work with thermodynamic diagrams, the kinds of things we want to figure out, like the stability, they're not really the right tool for the job. It's just the difference between stable and unstable is just too small on this diagram to just look at it and see it with your eye. And other things that we would do, other processes that we would do with this thermodynamic diagram, where like lifting and lowering air parcels and different kinds of diabatic and adiabatic temperature change processes and so on, that you would do with a thermodynamic diagram, it's just too hard to get them right on this STUVI diagram. The differences are too small. Just to draw an analogy here, this is kind of like saying, hey, I'm on a diet right now and I want to check my weight and see how I'm doing. And so I'm going to go out on the interstate to where there's a truck scale and I'm going to weigh myself and then I'll exercise and I'll go weigh myself again. Okay, technically a truck scale might be able to do that, but do you think the truck scale is actually the right tool for the job to measure your weight before and after you were on the diet or whatever? Unless, it's not made for that. Okay, it's just not the right tool for the job. The difference between your weight before and after you worked out or last week versus this week or whatever on your diet is too small for what the truck scale is for. It's just not the right tool for the job. And in the same way, I like the idea of STUVI diagrams, and there are things we can see on them, but it turns out we have better tools. There are better ways to figure out the kinds of things we want to get from a thermodynamic diagram. There are better ways to present the information that comes to us from a radiosonde and a weather balloon and so on. And that's what we're going to do next time when we're actually meeting, is we're going to be talking about some of these better ways to actually visualize this information. But for now, that's enough. That's all we needed for today. All right, thank you very much for watching this lecture. By all means, let me know if you have any questions, and I'll see you on Tuesday.